My name is Lemar Abdi, and I would like to welcome you to our presentation for our paper at the Onshore Workshop at MICAI 2025 titled Out of Distribution Detection in Medical Imaging via the Diffusion Trajectories. Existing approaches for unsupervised OOD detection generally fall into three categories, each of them having their own drawbacks. Distance-based methods, for example, need to store the training embeddings in memory. Density-based methods have the problem of assigning higher likelihoods to OOD samples compared to the training samples. Reconstruction-based methods are sensitive to noise. They can faithfully reconstruct anomalous samples, leading to false positives. Diffusion models are almost exclusively used with reconstruction-based methods. We could have an input sample where we noise it to a prior Gaussian in a 4-time diffusion, go back from the noisy sample to the generated sample in the reverse time diffusion, compare the reconstructions, and we assume that the higher reconstruction error would mean that the sample is anomalous. We assume this as the reconstruction-based methods train on the healthy samples. But what if we avoid the reverse time diffusion process altogether? The very process that introduces the limitations that we just discussed. How would the reconstruction-free approach even work for diffusion models? So only using the 4-time diffusion, we know that going from a sample to noise is governed by the stochastic differential equation. And we also can see and show that the trajectory from going to a data distribution to the Gaussian is unique for each data distribution. Thus, the Stein score of the marginal at each time step from a score-based or DDM-based diffusion model can capture the rate of change of the diffusion trajectory. And we say the Stein score as we are computing the gradient in data space, unlike the score function, which is the gradient in parameter space. Heng et al. Actually proved that the difference in Stein scores can be rewritten as the distance between two densities. The KL divergence for two distributions is thus related to the difference between the Stein scores. Now, knowing this, we only require one diffusion model that sufficiently can estimate the Stein scores for multiple data distributions. The anomaly score during inference is then computed as the rate of change and the curvature of the diffusion trajectory. And the curvature is basically just the time derivative of the Stein scores. We construct a medical OOD benchmark that splits the OOD task into Near OOD and Far-OOD, similar to the well-known Open OOD benchmark. We use the MedAmnes dataset, which contains more than 700,000 2D images from 5 different modalities at a resolution of 128 by 128. For near semantic OOD shifts, the majority class or healthy class is selected as the inlier set per benchmark. For Far-OOD, samples with great semantic shifts from other datasets or modalities are considered anomalous. In a one versus the rest approach, these are then averaged out. We obtain promising results across multiple benchmarks compared to the conventional reconstruction diffusion method with a latency of 940 milliseconds. We have an inference time of around 55 milliseconds due to only needing 5 denoising steps. Analogous to most methods in all baselines, the SBDDM is retrained for each benchmark, where the inlier sample of each benchmark and the training samples are sourced from the same training set. However, in contrast, the SBDDM-P results are obtained by only training on one large medical dataset. This is possible due to the fact that we only need to extract the correctly estimated Stein scores, and these will be unique for each dataset, regardless of the training dataset of the model that's used for the estimation of these scores. So we can actually do zero-shot OOD detection across different modalities. So are you interested in how this exactly works, or to what extent the training data affects performance, or do you just want to have a chat? Feel free to visit my poster at the workshop.